So, in the last class, we saw an example of how NMOS and PMOS transistors can be combined together to build a circuit which you could possibly have built with NMOS transistors themselves, but it would have been a way more messy. We saw a simple 4 transistor circuit that can be used to generate a bias voltage, a bias current, which is such that the transconductance of the transistor remains constant irrespective of supply voltage as well as temperature, right, and we derived the circuit from scratch. So, today we will see I mean the rest of the course we will basically be using NMOS and PMOS transistors together to come up with useful circuits, and like in the case with NMOS transistors, the simplest amplifier we started off was the common source amplifier, and likewise in this case also we will start off with the common source amplifier, except that we will to motivate the reason why this is necessary, I will talk about a common source PMOS transistor, and we will go from there. So, remember that eventually we are trying to build circuits where we are trying to build circuits with negative feedback, and the reason for doing that is to make sure that the closed loop gain or the closed loop properties of the system are largely independent of the properties of the transistor, and the way this is possible is by making the forward path gain as large as possible, right, ideally infinity. Of course, you can only get close, you can't make it exactly, I mean you can't make it infinite. Now, that basically means that the gains of the individual stages must be as large as possible, right. Finally, you want to get gain, and of all the 4 amplifiers that we have seen, right, the common source, the common gate, the common drain, and the transimpedance amplifier, the candidate which allows you to have the largest incremental gain is the common source amplifier, right. So, we would like to see how much gain you can get out of a common source amplifier. So, to see that as I said, a picture is worth 1,000 words, and since we are talking about PMOS transistors, let us do it with PMOS transistors. The same discussion would have been valid with NMOS transistors too, but since we just started off with PMOS devices, it helps to get some more intuition on how they work. So, I will discuss this with PMOS transistors. So, let us consider a common source PMOS amplifier. So, the gate is biased at some Vg, right. Let us not worry about how that bias came about, it could be a resistor string, it could be something else, and there is Vg plus Vi, some voltage, and this is some R. And so, as they say, a picture is worth 1,000 words. So, if we want to find the I mean Vi is a small signal, or an increment. So, first things first, if we have to find the operating point at the output, let us call that node X, which is also the drain potential of the PMOS transistor. How will we do it? If we want to find it graphically, what will we do? Okay. So, basically the idea is to say, we know that in at the operating point, the drain current must be exactly the same as that flowing through the, of course the source, but drain current must be the same as that flowing through the resistor, right. So, what should I do to get the operating point? I will plot ID as a function of Vx, that is what I need, correct, and I will plot IL as a function of Vx. The place where the two intersect gives me the, I will plot ID versus, I mean we know that ID must be equal to IL. So, I will plot ID as a function of Vx and IL as a function of Vx, and the two curves will intersect at a point. The x coordinate corresponding to that point of intersection will give me the operating point, operating voltage Vx, alright. So, let us now plot ID as a function of Vx. When Vx is 0, what is the region of operation of the transistor? The transistor is operating deep in saturation because the drain potential is way below the gate potential, right. So, what will be the current in the transistor? How will we find that current? Let me not confuse you by adding Vi. So, let us say this is Vg, okay. So, how will we find the current in the transistor? What is ID when Vx is 0? So, I naught is nothing but half mu p Cox W by L times the Vsg, which is Vdd minus Vg minus Vtp the whole square, alright. So, let us call that I naught, that is I naught, okay. So, I will go on increasing Vx, and what will happen to the current ID? It will remain constant as long as the transistor stays in the saturation region. At some point what will happen? As Vx becomes larger and larger, the transistor will go into the triode region. So, at what value of Vx will the transistor go into the triode region? Very good, Vg plus Vt, and beyond that what happens? The transistor goes into the linear region. So, what happens to the current? Current drops and eventually it will become 0 when? At what point, at what Vx will the current drop to 0? Vdd. And in this region, what region is the transistor operating in, Roy? When Vdd, when the current is 0, what is the region of operation of the transistor? It is operating in the linear region, right. Why is it not cut off? As he claimed earlier, Vdd minus Vg is greater than Vt. So, the transistor is not cut off. Just because the current is 0 does not necessarily mean that the transistor is cut off. It could be in the triode region, right. So, the transistor is indeed operating in the triode region, except that the Vds is 0 and therefore, the current is 0. Alright. So, the next job is to plot IL versus Vx. Okay. So, how will that picture look like? It will be a straight line passing through the origin. And what is the slope? 1 by r. Alright. So, what is the operating point? Yeah, the point of intersection, correct. The slope is 1 by r. The y axis of the point of the y coordinate of the point of intersection is what? I naught. So, now let us solve this challenging mathematical problem. Tell me what the x coordinate is? I naught times r. Okay. Correct? You would have said, Dave, what the hell is this? I mean, yeah, I would have told you this without drawing all these pictures, right? That's indeed right, but it will give us some intuition. Just hold on a second. All right. Now, to see what the incremental gain of the transistor is, and again we could have calculated it using the formula, but we'll as they say, a picture is worth 1,000 words. So, we'll draw the picture. So, if I increase the gate voltage by a small amount delta V, right, what happens to and I mean by incremental gain we'd like to see what we'd like to see is the change in the drain voltage due to a change in the gate voltage. That's what incremental gain means, correct? So, if I increase the gate voltage by delta V to find the new potential at the drain, what should we do? If you want to look at it on this graph, what should we do? This curve corresponds to the gate voltage being Vg. What should we draw now? We need to draw another curve corresponding to Vg plus delta V. Okay. So, the gate voltage is increased by delta V. So, what comment can you make about the current? The current has decreased. Okay. So, how much has it decreased by? Assuming it is a small signal, it is reduced by Gm delta V. Okay. So, again what happens? So, this characteristic will look like this, and again it will fall off when the voltage reaches Vg plus delta V plus Vt. Okay. So, this is nothing but I naught minus Gm delta. Let me use another color. What now? What is the new operating point therefore? Yeah, so that is this point of intersection, and that is nothing but I naught R. Well, that distance is nothing but Gm delta V. So, the output voltage is Gm R times delta. The voltage is shifted by that much, correct? Is this clear? And this is telling you two things. It is telling you that when you increase the gate voltage, the drain potential is decreasing by how much? GMR times delta. I mean, this is all stuff you know, correct? Alright. So, now if you want, so for a given delta V, alright, if you want more incremental gain, then what comment can you make? Then that basically means if you have more incremental gain, that basically means that that distance must increase. Is this clear? Alright. So, with this background, how will you increase the incremental gain if you want to keep Vg and the transistor the same? If you increase R, what happens? Well, you now have a curve for the load which looks like this, and as you can see visually, as you keep increasing R, what comment can you make? The change in the drain potential due to the same change in the gate voltage delta V is increasing. Is that clear? Yes, no? Alright. Now, if you get too greedy, what happens? You are saying, well, if I had R, I had some gain, I increased R, I got more gain. So, what if I increase even more? The transistor will go into the linear region, and you end up with this situation there, right, where as you can see visually the transistor has gone into the triode region, right, and you see that the gain, incremental gain has reduced. All right. Okay. So, now, so as you can see, the best bet for you is to make the resistor large enough so that the transistor is operating at the edge of saturation. All right. Okay. Now given this, and if you want to keep the drain current the same, right, remember I am not constraining VDD, I am not constraining VG, but I only want to make sure that the drain current remains the same. If I want to increase the incremental gain, what do you recommend that we do? Let us say we are already operating on the blue curve, so that we have the maximum gain that is possible with this VDD, correct. If I want to increase the gain further while making sure that the quiescent current in the transistor remains the same, what choice do I have? The transistor is the same, the quiescent current is the same, so the GM is the same, so that is not a choice. No. What can you do to this circuit so that the incremental gain can be increased beyond what we have right now, which is assumed to be the blue curve, right? R is chosen to be, let us assume that R is such that we are operating with the blue curve. Is that clear? Alright. I do not want I naught to change. So, and consequently GM to change. So, that remains fixed. If I want to increase the gain, what can I do? Increase? If I increase VDD and VG both by the same amount, what happens? Let us call that, so therefore now let us say the new VDD is VDD hat, right, which is greater than VDD, and the new VG is VG hat, which is greater than VG, so that VDD hat minus VG hat is the same as VDD minus VG. In other words, we increase VDD and increase VG by the same amount. So, what happens now? What happens to this picture? The curve will? Okay. So, basically now if we increase, I am going to exaggerate here and increase VDD by a really large amount. So, let us say I double it. So, this is VDD hat. So, what happens to the curve now? What happens to the black curve? It stretches and does that, right. So, this is for VG. What happens to the red curve now? It will also stretch, okay, and this guy here is VG hat plus VT, alright. Okay, so we have increased the VDD and VG by the same amount. Now, what should we do? You increase the resistance, right. So, if you increase the resistance, what happens? Right, this is the new resistance, correct, and as you can see, what comment can you make about the incremental gain? It will increase, correct. So, with this transistor having this GM, the only way of getting a larger incremental gain with a resistive load is to increase the supply voltage and increase the gate voltage by the same amount, so that the transistor still carries the same current, but you increase the resistance, so that even with the now with the increased VDD, you are operating now at the edge of the saturation region, So, then you will be able to get the maximum possible gain with this new VDD, correct, and that maximum will be much larger than the maximum gain you could get earlier. Is this clear so far? Alright. Okay. So, now using this strategy, if I have to increase the gain by a factor of 10, right, approximately how much would the VDD have to increase by? So, in other words, originally we had some VDD, we had some maximum incremental gain, correct. Okay. Now, if I wanted to increase the incremental gain by a factor of 10, look at the picture approximately and tell me how much must VDD increase by. So, if you assume that VGS is very small compared to VDD, alright, a VSG is very small compared to VDD, what does that mean? That this is very small compared to that, alright. So, using that approximation, what comment can you make if you wanted 10 times the gain? If I have to increase the gain by a factor of 10, what comment can you make about the slope of the new blue line? 1 over 10. So, what comment can you make about this distance in relation to this distance? 10 times. If this is very small compared to VDD and VDD hat, what comment can you make about the new VDD? Huh? Roughly 10 times. Is this clear or no? So, what is, I mean, this with this line we have some incremental gain, correct. Now, we want to get 10 times the incremental gain. So, what should we do? We increase VDD to some large value VDD hat, right. Now, since the incremental gain is increased by a factor of 10, what comment can you make about this slope versus that slope? This distance is the same. The incremental gain is basically this distance, and that has increased by a factor of 10. What comment can you make about the slope of the second blue line? It will be 10 times smaller, correct. So, if the slope of this blue line, let us call this 1 by r, and this is 1 by r hat, the slope of that second blue line is 10x smaller than the first blue line. Is that clear or it is not clear? Okay. Now, what comment can you therefore make about this distance versus this distance? Okay, let us you have a triangle, okay. This is now high school algebra. You have a triangle with some slope. Now, you have a triangle with a slope which is 10 times smaller. I am asking you, if I call this triangle ABC and I call this triangle ADE, what the question I am asking you is, what is AD by AB? BC by AB, tan inverse actually, but it is fine. Okay, all right. The slope of the second line is of AE is and BC and DE are the same. Okay, all right. I am telling you that the slope of AC is 10 times higher than the slope of AE. All right. So, now I am asking you, what is AD by AB? So, so AD is 10 times, you understand this much, okay. Now, with this background, now tell me, this slope is 1 by r, this slope is 1 by r hat, which I tell you is 1/10 the slope of the first blue line, right. Obviously, these two heights are the same. So, I am asking you the question, what is this ratio of that to that? it will be 10 times. Is this clear? Alright. Now, if this is very small compared to this distance, then you can neglect those small extras and you can roughly say that if you want to increase the gain by a factor of 10, if you want to increase the incremental gain by a factor of 10 while keeping the quiescent current the same, then the only way to do it, if you want to have a resistive load, is to increase the VDD by a factor of 10. Alright. Now, if you want to increase the gain by a factor of 100, you need to increase the VDD by a factor of 100, correct. So, basically as you can see that this is a, a pretty impractical thing to do. So, if you had a gain of if your common source amplifier had a gain of 10 and you wanted to increase it to I do not know say 100, okay, and if the original supply voltage was 2 volts, you need 20 volt supply to be able to get an incremental gain of 100 if you use a resistive load, right. And if I want a gain of which is 1000 times larger, this VDD hat will have to go into LHL. Okay. Alright. So, you see the problem, alright. Okay, and this is a terribly not at all efficient from a power point of view, because the power you will be dissipating is VDD hat times IL.